Hello, hello, hello. We're back live and sound on, lights, camera, action. Okie dokie. Hopefully everybody had a nice lunch. Hopefully we're all well supped and fed and feeling a little more plump and energized. Right, continuing on with this sort of broad brush theme of mechanics and how sort of the world of macro physics works, things that we can interact with day to day. We're looking at forces, momentum, and equilibria. We're aiming to finish at 2, so an hour and 15 minutes on this topic, and we'll have a little break before pushing on to waves. Okie dokie, we will be talking about equilibrium. So an object, when it's at rest, we're used to thinking that means the forces, the linear forces on it are balanced. It's not moving up, it's not moving down, left, right, fine. But there is another type of equilibrium it is in, and that is rotational equilibrium. It's not spinning clockwise or anti-clockwise around any axis at all. And you can consider those two parallel systems as running in analogy to each other. And it's a pet favorite topic of mine. We'll be talking a bit about Newton's laws, just refreshing our memory of those, and the equilibria of multiple systems. We'll then talk about free fall and terminal velocity, which I know some students can get a little bit confused about. Let's iron out those creases and continue on. Acceleration due to gravity, drag force, and that dreaded terminal velocity. And then finally, we'll be talking about some collision questions, an absolute classic of the genre. Okie dokie. Up first, equilibrium. Like I said, we are perhaps a lot better practiced in terms of linear forces, balancing those out. Is it going up? Is it going down? Left, right? What speed? With what force? But until A level, we don't massively focus on spinning objects, even though that's just as common and just as important a part of our everyday lives. After all, the invention of the wheel was a classic turning point in physics. Right, the principle of moments then works very much similar to equilibrium for linear forces. The moment of a force about a point is equal to the product of the force and the perpendicular distance from the line of action of the force to that point. What do we mean by that? If I have an object which is capable of spinning, either apologies. You know, apparently I hadn't shared my screen. That should be fixed now. Thank you for whoever let us know. It's odd, you know, you find yourself a physics teacher for X amount of years and then you fall at the last hurdle. Right, as I was saying, the principle of moments is really just talking about the definition of a moment. Different physicists across different countries use different words for the moment. It's also called torque, Torque. Americans tend to use that word. It's a little less ambiguous because obviously the word moment obviously means other things in plain English. And the moment of a force is a linear force applied a perpendicular distance d from a given pivot. Okay. Now, if that's all well and good, if the force is perpendicular from our pivot down here. Sorry, if I get my pen out again. But if it's not, say, for example, the force was at an angle here, you would, of course, need to take the components of that. We've written FD sine theta. So that will be the angle here, theta. I.e., it's the angle between, if I draw this force up here, for example. So sort of same arrow. It's the angle between the force and D. Fab. So if the angle, if there's no difference between them, it'll be sine 0, which is 0. So you won't experience a torque at all. If the angle is 90 degrees, if it's right angle, you'll end up with moment is just equal to FD, which is nice and simple. Okie dokie. Right. The principle of moments states that for a body in equilibrium, the sum of clockwise moments about a point is equal to the sum of anti-clockwise moments about the same point. This is directly analogous to saying when we talk about linear forces for an object at rest, all the upwards forces have to equal all the downwards forces, except instead of talking about up and down, we are talking about clockwise and anti-clockwise. It's a direct analogy. So everything you've learned before, you can apply once again. Okay. So in this case, we've got what looks like a plank of wood. It's balancing on our pivot. Again, Americans have different terminology for this, but you might see it used in some textbooks. If you do wider reading about the syllabus, they're likely to call it a fulcrum, which is a slightly cooler word, perhaps. Who knows? I'll leave that up to you to decide. So where's the first torque that's going to apply here? We've got our plank of wood. That obviously in itself has mass. Where is that mass going to be acting? It acts at a position we call the center of mass. That is not guaranteed to be in the middle of it. For example, you could have a plank with a non-uniform density. So one end is heavier than the other. Maybe one end got wet, and so it's absorbed water. And so its density's gone up a little bit. And the other end is dry as a bone. In this case, it does look like we've got a slightly asymmetric plank of wood because its center of mass, indicated here, is not in the sort of geometrical center of our plank. Okay, so we have the mass of the wood multiplied by G, and that's our downwards force exerted there. And we will call that distance D2. What else have we got going on? We've got a mass over here. Let's call this mass wood and mass block. We've got it hanging right off the end of our piece of wood, a distance D1 away. The principle of moment says if this plank is in equilibrium, i.e. everything's stationary, it's not, rotating either way, we would have to say then that mBg times D1 is equal to mWg times D2. Cancel the G's. The mass of each mass multiplied by its distance away from our pivot must be equal. Oh, pardon me, that was an accident. Now I chose to take pivots around, take moments around the pivot in this case. Partially because that feels like the obvious place to do it, but we'll see later on that built into the definition of moments, given that a moment is defined as force times by the perpendicular distance away from whatever pivot you are considering, built into that definition is an implied choice of pivot. The truth will turn out to be that it does not really matter what pivot you choose. You could have done this whole question choosing this point over here as your pivot. The maths would work out such that it would all balance, but you'd then have to consider what's the contact force being applied at the pivot there, which makes things a little bit more complicated. Right, let's have an exam question to get us back down to the ground. So consider the following diagram showing an 8 meter long, 2 kilogram irregular beam. That implies that, just like our plank in the last question, it is not uniform. supporting a 2.5 kilogram block, suspended by 2 taut strings from a support. The tension in the right-hand string is 48 newtons. The system is in equilibrium. Ah, we love to hear it. Determine the position of the center of mass of the beam in the diagram. Okay, this is a calculation question. We're looking for a numerical answer, 3 marks. So roughly about 3 steps in our calculation. Context is equilibrium, and they give us some lovely numerical values. We're looking to determine the position of something. So your answer had better be in meters. We've provided a diagram. If the examiner doesn't provide a diagram, I recommend doing a quick jot. Always helps. So they tell us the length, 8 meters. They tell us its mass. Great. They tell us the tension here, and they tell us the mass here. Do they tell us this 6 meters? Let's say if they do give us that information. Because this diagram was also given in the exam. I see. Right. Okay, good. So they've given us some extra information as well as in the text. So watch out for that too. We don't mind how we get it, as long as we have the information, we're happy. Right, select a point about which to take moments. I said you can technically do all your moment questions by taking the pivot wherever you like. However, there is often a tactical, strategic element to this choice. In this diagram, we have how many forces at play? We've got tension here, tension here. Somewhere along here, I'm going to draw it in an intentionally sort of not obvious place. Somewhere there's the center of mass of the beam, and you've also got this block here. So there's 4 places where forces are being applied. I always recommend choosing one of those places, because wherever you choose, if I choose my pivot, for example, where the block is, I then don't need to worry about what the, oh, sorry, I've accidentally been pressing the eraser. I don't need to worry about the moment of that force because it's 0 meters away from my pivot. Okay? So although there's 4 forces, by choosing my pivot at the location of one of those forces, I can essentially do a calculation that only has 3 moments, 3 non-zero moments. However, I'm interested in the location of this center of mass. I've been given the position of D anyway, and I've been given information about this. The only force I don't really know anything about is this one. Therefore, I think it is by far wisest to choose our pivot there. Therefore, we don't really need to worry about, however much force this is. It'll be factored into the rest of the question. Okay, choose the left edge of the beam. Consider the effect of each of these forces. Force 1 here, 2, and 3. What effect will they have? Is the beam likely to turn clockwise? Yes, these 2 forces, forces 1 and 2, they're acting downwards. If they had their way, the beam would swing and fall down. The third force, however, can be recruited into the army of the anti-clockwise. Because if that was the only force acting, the beam would lift up like the drawbridge of a castle. Okie dokie. So the clockwise moments, we've got the mass of the beam times gravitational constant. That's our force. That's the weight of the beam times the distance, wherever the center of mass, the distance to the center of mass of the beam. That's weight number 1. And weight number 2 is mass of the block times G times the distance away from it. That is 6 meters D. Okie dokie, factor in our values given. and we have an expression in terms of the center of mass of the beam. We now know that's got to be equal to all the anti-clockwise moments around the beam. For the anti-clockwise moment, we've just got our force on the right side of the beam. We've been given T. T is 48, so that's good. We know what that is. The length of the beam we know, good. We've also been given this angle because do not forget that we need to take the perpendicular. It's only the perpendicular component of the force that contributes to the moment. So sine 45. Okay, that's an exact numerical answer, 271.5 Newton meters. Moment, take a note that the units of moments are Newton meters. And then apply, last but not least, the principle of moments. Our expression in terms of the center of mass is equal to a set number. We can rearrange to get the position of the center of mass. It is 6.3 meters from the left edge. Fab. Okie dokie. So that was a brief dive into angular kinematics and dynamics. But there'll be more of that in the year 13 syllabus. Now, floating back down to linear forces, it's worth recapping Newton's laws. He's got 3 regarding motion, but obviously Isaac Newton was busy doing all kinds of physics. The first one, an object at rest or moving at constant velocity will remain so unless acted upon by a resultant force. So, on the same slide, we've got Newton's second law. The resultant force on an object is equal to the product of its mass and acceleration. So, in other words, pardon me. In other words, F equals ma, everybody's favorite one to remember. Rearranged, the acceleration on an object that's experiencing a resultant force is that force divided by its inertial mass. Fab. So, for example, a satellite, there's only one force it experiences, downwards, therefore its acceleration is also downwards. Sorry, I've drawn that slightly slanted. Acceleration is also downwards, despite the fact that its velocity is constant horizontally. And indeed, that horizontal velocity, it will be constant as per Newton's first law until a resultant force acts horizontally upon it. Maybe it'll sort of collide with the atmosphere and there'll be friction, or maybe it'll fire its thrusters and that'll interfere as well. But until that day, it'll carry on happily at constant velocity. Fab. So you've got Newton's first and second laws both applying in the case of a satellite. The third law is a slightly more technical statement. Consider 2 objects, fictitious objects, A and B. If A exerts a force on B, then B exerts an equal and opposite force on A. When I was talking earlier in the exam technique session, I said that there are certain phrases the mark scheme loves. And whenever you're talking about Newton's third law, please mention equal and opposite in some combination, those 2 words, equal and opposite. The way we've written it here will exert a force of the same type of equal magnitude in the opposite direction of A. That's a lovely way of putting it. But even if you're in a rush, include the phrase equal and opposite, please. Right, so what's a good example of this? If, for whatever reason, my astronauts in the satellite chuck an apple out, there's an apple falling to Earth, we're fairly happy with the idea that it's going to accelerate pretty quickly towards good old planet Earth. However, what Newton's third law asserts is that whatever the weight of this apple is, that same force will also act on the Earth towards the apple. However, of course, The acceleration will be very different for the two. You can say, look, the weight on the apple is equal to the force on the earth. But of course, by Newton's second law, that's equal to the mass of the earth times whatever its acceleration due to this interaction is. And it's also going to be equal to the mass of the apple times whatever its acceleration is. But of course, the mass of the earth is huge and the mass of the apple is comparatively tiny. And so by comparison, the acceleration of the apple is going to be huge and the acceleration of the earth is going to be tiny. Barely noticeable, in fact, which is why we don't see, you wouldn't expect to observe the earth sort of massively going out of its way to meet an apple. Another good example, collisions. We'll talk about those later in this session. In a collision, the same force acts on each object, even if object A looks bigger than this one, looks more massive than B. The same force will act on both of them. It's just that because they've got different masses, it'll change their accelerations inverse to their masses. Object B has smaller mass, so it's going to have a bigger acceleration going away from the collision generally. Okie dokie. Hopefully that's not too confusing. Hopefully that's all clear. Let's do a little exam question then. A space probe is traveling to Mars at a constant velocity. Upon approaching its destination, the probe ejects its fuel tank backwards. If you weren't already thinking Newton's third law or Newton's laws in general, they make it explicit here. Describe and explain are our command words. So state what happens and then tell us a little bit of physics that explains it. With reference to Newton's laws, how the probe's motion is affected by ejecting the fuel tank. Hopefully, there's only two marks question. I should point that out. So just 2 bullet points should do. What happens and why? Right. It says Newton's laws, but you should hopefully identify we've got 2 objects here. I dare say an object A and an object B. We've got the rocket and its fuel tanker. So it's Newton's third law we're talking about. First point, on ejection, by Newton's third law, the fuel tank exerts a force on the probe equal and opposite to the force that the probe exerts on the fuel tank. Great. You're essentially stating Newton's third law, but just applying it to this specific context. But that doesn't mean the other of Newton's 3 laws stops applying. By Newton's second law, the probe therefore accelerates forward as the engine is ejected at a rate proportional to the resultant force. Got 2 bodies. Way. That's the sort of before picture. And then afterwards, the rocket carries on and my fuel tanker is sadly shed into the ether, into space. Fab. Right. Pressing swiftly on, how are we doing for time? Right, the equilibrium of systems. So we talked about equilibrium in a rotational context, but let's talk about the linear context. Still important. What does it mean to be in equilibrium? Just as we said that equilibrium of moments means that the rotational, that the clockwise and anti-clockwise are balanced, here we're saying, look, there's no resultant linear force on the system. So any forces up are matched by all the forces acting down and vice versa and side to side. We can use the fact that a system is in equilibrium to determine the forces acting by balancing forces in each direction and applying the principle of moments about different points. Right, so I've talked, I think pretty much exclusively today, about up and down, resolving our points up and down. But it should also be noted that as long as, I can change my ink color, that'll be exciting. Okay, as long as you're resolving the forces in 2 perpendicular directions, they'll always act independently, just as if we're talking about vertical and horizontal. So here, we've got an inclined plane. It makes sense to me, therefore, instead of talking about vertical and horizontal, it might be more sensible to talk about parallel to the plane. And perpendicular to the plane. And we'll resolve our forces in that direction. So we've got, what forces have we got? We've got tension in this rope. We've got the weight of the block, of course, that never stops acting. And we've got the normal contact force of the slope that is acting on the block, which you can call N or R, I don't really mind. And if we're dragging this up, perhaps we also have friction. If it's stationary, maybe we don't have friction, and the resulting tension and normal contact force will have to adjust to meet the demands of that. But for now, okie dokie. If we say this slope is at theta, we can deduce that this is also theta. We'll be able to resolve our forces, and we can say, look, hey, W cos theta must equal R. That is by resolving the forces parallel to the slope, perpendicular to the slope. You've got R acting upwards, and the one component of the weight acting there. And if we consider the forces parallel to the slope, we'll have acting upwards up the slope. We've got tension, and that will have to be sufficient to meet the friction and the component of the weight acting down the slope. Okay. Hopefully that's not too confusing. For an object at rest on a slope, we can resolve forces parallel and perpendicular to the slope and determine the forces acting on it. I can see now, having turned the page over in my notes, that maybe I've spoiled a little bit of the surprise of this slide. Parallel to the slope, just as I said before, T. In this case, they've got the friction acting the other way, which implies that that's because this block is actually being lowered down the slope, and so the friction's acting to oppose its motion. Okay, that's a nice twist. So instead of the friction acting on this side of the equation, it's going to turncoat. It's going to join the tension in acting up the slope, and that is going to have to be equal to the weight, the sine theta component of the weight mg. Perpendicular to the slope, similar to last time, R is going to have to be met by the component of the weight that is acting perpendicular to it. Okay, exemplar calculation question. I'm just going to switch back to my beloved red pen. A uniform shelf of mass 4 kilograms is attached to a wall by a hinge at the point of contact and by a supporting cord of length 1 meter at its far end, which makes an angle of 60 to the horizontal. There's a normal contact force at the hinge, which has an unknown vertical and horizontal component. The shelf is in equilibrium. Good, love it. Calculate, there's our command word, the total magnitude of the contact force in the hinge. Just the magnitude. We don't necessarily need to know the direction, but this is a 4-marker question, so watch out. That implies it's not necessarily going to be quite as straightforward as we might once have hoped. Okay, good diagram always helps. As we are told this angle is 60. I know it doesn't look like it, but that's what the question says. Yep, makes an angle of 60 to the horizontal. We are told the length of this rope is 1 meters. What else are we told? Oh, the mass. And we're told, although I was remiss in not underlining it, we're told it's uniform. Also very helpful. So 4 kilograms, so 4 times G. And we don't necessarily know its length, but for now, let's call it capital L. Why don't we? Okie dokie. I think that is all the information we're given. We know that there's going to be horizontal components. Let's call it RV and RH. And we know it's in equilibrium, which is fantastic. There's a tension acting here. Let's call that T. All that really remains for us to do then is to work out a few of these dimensions. Straight away, I'm thinking, well, actually, we're not given L, but we can work it out. There's a right angle triangle here. We're given the hypotenuse. So L is going to be 1 meter times cosine 60. Yeah. Which is nice. You can plug it into your calculator. Or a few of you might know off the top of your head. Well done, you. But for now, I'm just going to write it as cosine 60, just so we're all on the same page. And you can take moments around the hinge. We're told it's in equilibrium, so we know all the clockwise ones, all the clockwise components are going to equal the anti-clockwise components. If we take moments around the hinge, that's a great choice because we don't need to consider the rotational effects of these two forces because they are 0 meters away from our pivot. So ignore them. Huzzah! Instead, we'll need to calculate the moment of this force, the weight of the wood, and the effect of the tension only. So there's just 2 forces at play, which is awesome. Right. So half the length of our wood, L over 2, times the weight, has to be equal to the full length times the tension times sine 60. Rearrange for the tension, plug it all in, and realize that, well, we didn't actually even need to work out L. It was all very clever of me, of us to work it out. But in fact, the L's are going to cancel out in this equation. So don't stress yourself. And the tension we work out on seem as if by magic almost. We've got the tension without doing much further work. And that is the powerful insight that moments can provide. Okay, tension T is in the bag. Up next, we want to look at the linear picture. We've done as much as we can do with our rotational dynamics, and now we're looking at linear stuff. So, just a tiny little diagram. We had our tension along here, we had the weight here, and then we had our 2 components here. The horizontal components, it's only going to be T and RH that contribute, and they're in opposite directions. So RH is equal to the horizontal component here, which is T cosine 60. Fab, we know what T is, so we can work out what RH is. It's 11.33. Vertical forces, we now have 3 contenders. We've got RV, we've got the weight, which is 4 times little g. That's 4 times little g, not 4 grams, by the way, just to clarify. And then you've got the vertical component of our tension. RV and T act upwards and the weight acts downwards, so they've got to balance that way. All of those we know except RV, so rearrange for RV, and you end up with 19.62 newtons. Neither of those 2 values seem wild to me. Find the magnitude of the force. Well, we've got 2 components. We know what these are now, so it just remains to use Pythagoras and recombine them, add them in quadrature, and you end up with 22.7 newtons. Okay, end of question. It asked for the magnitude of the force. It wasn't necessarily concerned with the angle at which it's acting, So don't bother, using tan theta or sort of trying to work out an angle at which the normal contact force works. The question didn't ask for it. Okie dokie. So perhaps the only difficulty or the main difficulty when thinking about equilibrium questions is that you've now got, I guess, 3 tools to tackle those questions. You can resolve things vertically, resolve them horizontally, but you can also consider the moments and think of it in terms of rotations, which is nice. Okie dokie. Pushing on to freefall and terminal velocity. We've already used it several times today and perhaps taken it for granted, but hopefully everybody will be familiar with Galileo and his experiment with dropping the 2 balls off the Tower of Pisa, one of a dense material like lead, one of a less dense material like wood, drops them both off. They've both got the same aerodynamics, so that's not a factor, that's a control variable. And they both hit the ground at the same time, even though one is so much heavier than the other. And that's because all objects accelerate. Their acceleration due to gravity is the same, or at least at the surface of the planet. Obviously, if you go off into space, the gravity will be at a different level to what it is on planet Earth. But for the vast majority of human experience, that's exactly where we'll be. So, as the slide says, all objects neglecting air resistance, and do remember that that is a fact. If you drop, for example, if you'd done that same experiment, but they hadn't been the same shape, if you'd had like a flat discus and the other one was a thin pencil and you drop them, then they would hit the ground at different times because air resistance would affect them differently. But neglecting air resistance or factoring it out by having the same shape, they fall at a constant rate in a gravitational field regardless of their mass. The descent of cannonballs rolling down ramps is the slightly more grounded experiment he did. This constant rate, by measurements, we've shown it to be 9.81 meters per second squared. If you think that's very specific, that is because it is particular to planet Earth. So don't go applying that if you're given a question where it takes place on the moon or something. Please don't go using 9.81 because it's only true of planet Earth. We can demonstrate the principle of constant acceleration due to gravity by doing a tribute act to Galileo, or if we're in our classrooms, we can resolve a force diagram for an object using Newton's second law. Okie dokie, so force diagram, as always, there's weight. That is equal to mass times little g. But, so the force is the weight. But this also has to equal the mass times the acceleration. So F equals ma applies generally to forces. The so-called inertial mass of an object. And the force in this case, perhaps I should write this equation actually the opposite way around. So it's F equals ma. And then I'm clarifying that in this particular case, we're talking about gravity. And this is what we used to call the gravitational mass. And scientists for a while used to ponder, well, is the inertial mass fundamentally the same as the gravitational mass? And it all gets a little confusing. We don't generally talk about it at A level. It's not on the syllabus. But for those of you interested, and it turns out, well, hey, these two things are the same, the inertial mass and the gravitational mass, and you can cancel those two. And you can say, look, G literally is just the acceleration from Newton's second law associated with gravity. Nice. Makes things a lot simpler. It would be a bit of a headache if we had to start using two different masses for each object. All right. Okay, this is a bit of a nightmare question, isn't it? One sentence. You look at it and you think, yes, that's probably only 1 mark. No, sirree. 4 marks. Plan an experiment to measure the acceleration due to gravity. Oh, terrible. It's an experimental analysis question. Not as bad as it could be. It's only 4 marks rather than 6 marks. But the saving grace is that it is a plan question, so you can at least get at least 1 mark from drawing a nice diagram. As our slide says, make sure it's neat and easy to interpret. We don't want, it doesn't have to be artistic, but just, you know, clean straight lines, nice and labeled. That will stand you in good stead. And we want to detail our measurements. So if you are doing a question to measure the acceleration due to gravity, you might draw something like this. This is quite an advanced example. Clearly, I think in this case, we are looking at an electromagnet, just as a method to drop our ball. You've got yourself a ruler or a rule. The difference between a ruler and a rule, I'm reliably told, is that a ruler has like a little bit of extra plastic at the end, where there isn't, you know, there aren't the gradations, whereas a rule ends at 0. There you go. I didn't learn that until I was, you know, out of uni. So if anybody ever asks you, you can blame me. Right, in this setup, this looks to me at the bottom like a light gate, or it's linked to a timer. So we'll trigger our ball's fall from rest using an electromagnet, and it will fall and break our light gate, and that will set off our timer. Right, one more. 1 mark for just saying drop a small ball for which we can neglect air resistance from a height. Measure the height using a meter rule and measure time using a stopwatch timer. Sure, you don't have to have an electromagnet. You don't need to be fancy with a light gate. You can just do it with a stopwatch. The mark scheme for these 4 to 6 mark questions, as we saw earlier in the day, they're quite loose. They tend to say things like, any sensible suggestion. So as long as you're not proposing a sort of elaborate Wallace and Gromit style machine to measure the fall of this ball, generally, and there's a clear diagram, then generally you should be okay. Use a stroboscope, which flashes periodically. Okay, this is an alternative method instead of just using your timer. That's a very niche method. I've never seen a student write that before, but yeah, it'd work if you just film the descent of your ball and have a time signature in the bottom of your video. You can also just analyze it that way. Have the ruler in the background, note off at certain times. That'll work. Or have ball fall from electromagnet onto trapdoor, which breaks time switch. That's what we had on the previous slide. Okie dokie. So I think those are supposed to be 4 alternatives. Plot graph of distance against time squared. Why would we choose that? And measure acceleration due to gravity. Well, it's because of Suvat, really. It's if we're plotting distance against time squared, we're thinking of this Suvat equation, half at squared. U is 0 because we're dropping it from rest. So this should be at play. The acceleration is the thing we're trying to measure. Should be g, but our experimental value might be different. So if we plot s against t squared on the y-axis, so y equals something times x. That something should be equal to half g. Yeah, so just say, use that equation to determine g. Fab. So it's not too scary. Don't be scared too much when they say plan an experiment. And also, ultimately, there's only so many experiments that they can ask about, really. So, how are we doing for time? We said we would take a break at 2, so we've got half an hour. Okay, we should be fine. Often we can't neglect the effect of air resistance. We've been living in a dream world up till now, where we're saying, air, who needs it? But obviously that's not realistic. Drag is a resistive force for anything moving through a fluid, and a fluid can be liquid or gas. And the magnitude of it depends on the viscosity of your fluid. It depends on the speed through which you're going through it. And it will also depend on the cross-sectional area, if it's a large shape versus a small shape, but also the aerodynamic properties of it. That's why F1 cars are shaped that way, for their aerodynamic properties. Obviously, there's other stuff going on. They're trying to redirect the air upwards so that by Newton's third law, if as the car progresses forwards, the air goes upwards, that means the car is forced down, so it can get more friction and stay on the road. And it's all very exciting, I'm sure. For any F1 fans out there, plenty of physics at play. Right, coming back down to Earth again. As an object accelerates under a driving force, its velocity increases. Therefore, the drag force on the object also increases. Yep, that stands to reason. I believe in your formula sheets, you will nearly always have, there's an equation for drag, which sometimes comes up in exams, but it's not normally one of the more popular topics. Eventually, the drag force balances the driving force. The object is now in equilibrium. Nice. Okay, so yeah, this is a sort of chronology, a short history of fast objects. If you are stationary, there's no cause for friction with the air. There's no cause for air drag. As you start moving, well, if you're at a low velocity, there's still not going to be that much drag. The amount of air you're displacing per second is not a huge amount. And yes, air has some mass, but it's not as massive as if you were, moving into a wall or a person or whatever, or a vat of honey or something else that's far more viscous and tricky to move. But the faster you go, the larger a volume of air you're moving and having to displace per second. After a while, that does stack up. According to Newton's first law, the object stops accelerating. Okay, so yeah, eventually you will reach a velocity such that you've got your driving force, accelerated down to the max. At first, there'll be no drag when you're at low velocity. And then as you speed up a little bit, there'll be some drag. And then the final phase of this little story, the drag will have increased until it matches your driving force, at which point there's no resultant force, and therefore F equals ma. If there's no resultant force, there's no acceleration. And so you've reached your max velocity. You can't go any faster. It is literally your terminal velocity. An object at rest or moving at constant velocity will remain so unless acted upon a resultant force. There's no more resultant force. Therefore, you are traveling at constant velocity. Sad times for anyone who wants to, go faster and faster and faster forever. Okay, let's look at an exam question. A parachutist jumps from an airplane. This is as soon as you see that, you should probably be thinking, it's terminal velocity. After they've reached terminal velocity, the parachutist pulls their parachute. Describe and explain, again, that famous double act of command words. Describe and explain with reference to the forces acting on the parachutist, the motion of the parachutist falling under gravity. So tell me what you will see. Let's describe. will the velocity decrease? Will the acceleration decrease? La-di-da-di-da. And then explain. Tell me about drag. Tell me about how the forces are changing. Tell me, tell me how the acceleration is changing. The motion of the parachute is falling under gravity before and after they deploy their parachute. 5 juicy marks. Okay, remember, keep it to bullet points. I don't necessarily need the life and times of a parachutist. Each point should reference a change in motion. Yeah, I think that's reasonable. If you're asked to narrate the chronology of this, just sort of do it in chronological order. Keeps it nice and simple. Include both for full marks. I assume it's referring to describe and explain. Okie dokie. So, immediately after this fella has been dumped out of his plane, and it looks like he's a little bit surprised. Right, you're falling out of a plane. The parachute has yet to be deployed. You'll accelerate under gravity. Point number 1. Might seem easy, but yeah, you get a mark for just saying that you fall. Basically, you accelerate under gravity. As the parachutist accelerates, so its velocity increases, the magnitude of the drag force opposing this motion, or their weight, or their acceleration, whatever, increases. I've written the drag is proportional to v squared. I referred earlier to an equation in your formula sheets, your formula books. I believe that is the one they give you. Ultimately, aerodynamics is quite a complex topic, and it's not particularly well understood even by professionals. But when you're going at sufficiently high speeds, it's roughly proportionate to v squared. But that's not an essential part of the answer. If that bracketed bit wasn't there, they'd be scoring that mark anyway. The acceleration decreases until the drag force is balanced by their weight. Yeah, that's true. So if this sounds a bit confusing, stage 1, their velocity is very small, if not 0, but the acceleration is the full whack of 9.81. After a while, their weight is still the same, but there's a drag force against them, so the resultant force is smaller, and so the resultant acceleration is smaller. So their acceleration is now a bit less than g, and then after even more time, the drag equals their weight, and in fact there is no acceleration. Acceleration is 0. They've reached terminal velocity, and that is the story so far. But then suddenly they release their parachute, and so at the top I'm sort of talking, this is the picture in terms of acceleration up here. If over on the right side here I talk about force, before parachute, forces are balanced. Way, we've got the weight, we've got the drag. After the parachute, the weight stays the same, but the drag actually temporarily becomes huge. And so the resultant force is suddenly up. It's going upwards. And therefore you're actually accelerating upwards. And if you're suddenly accelerating upwards, like in an elevator, if it was really fast going upwards, you'd feel a sort of your centrifugal force, your inertia would mean that you'd feel slightly squished. And if anyone's been parachuting, when you deploy your parachute, you suddenly feel you kind of slam into your harness. And that is this sudden burst of acceleration upwards. Now remember, just because you are now accelerating upwards, that just means your velocity is changing to orient itself more upwards. That doesn't mean you're not still falling. It just means If you were going down, if you're falling to the earth at 100 meters per second, if you're accelerating upwards, it just means after the next second, you'll be still going down, but you'll be going down at 90 meters per second, and then 80 meters per second, and 70 meters per second. You're still going down, you're just going down slower. Okay. The cross-sectional area has increased. Yep, big parachute, and therefore the drag force also increases. The parachute just decelerates, or I've phrased it as accelerates, sort of against his motion. Same thing. The parachutist decelerates until they reach a new, slower terminal velocity. Yes, after a while. Yes, the cross-sectional area has increased, so D temporarily leaps up massively. You can consider these diagrams as a sort of story in themselves. But after a while, because you're decelerating, you'll be getting slower. And so that element of the drag depends on your cross-sectional area, but it also depends on your velocity. If you start to decelerate, then this drag force will also start to come down until once again they are balanced. The difference is they will now be balanced at a different terminal velocity. Okay? Where they're quite right to say that that terminal velocity, the new one, is lower than the old one. Okay? I know students do find that a bit confusing. And I think it is easy to lose track of. If you have any questions, do just message us on Facebook or on the email seminartutor@snapproviders.co.uk. I know a few of you have been getting in contact with our wonderful side tutors, and we appreciate that. So keep it coming. It's the best way to learn. Right, now for something not completely different, but a little bit different. Let's talk about collisions. Let's talk about momentum, specifically impulse. Okay, impulse is again one of these words that physicists have a very specific meaning for, and in everyday use, if I say you give something an impulse, or maybe you feel an impulse to do something, it's a sudden urge. So, you can kind of see where the physicists are, what they're getting at by calling this impulse. When physicists talk about impulse, what do they mean? They mean a change in momentum, essentially. So, this is what they mean. How fast you change momentum is deeply linked, is in fact equivalent to a force. If you rapidly change momentum, it will have to be due to a force. And if you apply a force, it will cause a change in momentum. So it's always actually slightly a bit of a historical lie every time we say that Newton's second law is F equals ma. First of all, because it's not always true. It's only true when mass is constant. What Newton actually wrote, and we're going to reverse derive it here. We know that acceleration is the rate of change of velocity, so a change in velocity or a change in time. So we can rewrite Newton's second law as F equals m delta v over delta t. And you might spot then that for constant mass, this is the same as a change in momentum. Because momentum is mass times velocity if mass isn't changing. So for constant mass, then delta P is equal to m times delta V, i.e. F is the change in momentum over the change in time. What we have in the bottom left. So the slight creative use of truth that physics teachers deploy, you know, with your best interests in mind, of course, is to start with F equals ma and then derive this in the bottom left, where the historical truth is that Newton wrote this, and that is the actual expression of Newton's second law, truly. But don't write that necessarily for your A-level exam. And that's true in all cases. And when you get to, if anyone chooses to do physics at uni, you'll explore the case when mass isn't constant, as is the case for rockets. Rockets, their mass is changing all the time because they are shedding so much fuel. They're burning it up and ejecting it out their back. And so the rocket equation is actually just it's actually just a specific application of Newton's second law, which is awesome that Isaac Newton in, you know, what century did he live in? 16th, 17th, something like that. Could write an equation that basically determined how rockets work. Fab. Right. Anyway, slight detour. Force is equal to the rate of change of momentum. The faster you change your momentum, the more the force. So the classic application of this is car crashes. You're driving along in your mobile and suddenly you hit a wall. You are going to want to reduce the force on yourself. If you want to reduce the force on yourself, you're going to want to, there's not much you can do about the change of momentum. You're going at whatever speed you were going at, and then suddenly you're going to be going very, very fast. You're going to be finding that you're traveling at 0 miles an hour. The thing you can change is the time over which it happens. And that's why cars have a crumple zone to kind of try and extend that bit of time by as much as humanly possible. More on that later. In fact, it's our next exam question. But before we get to it, the change in momentum. Yeah, sorry, I've already given this slide away. I've got a terrible knack for getting overexcited and then guessing and getting ahead of myself. But yeah, the impulse is equal to this change in momentum. You can also calculate it as the force applied multiplied by the duration over which that force is applied. If I apply a force to a box for 3 seconds, multiply the newtons I put in by 3 seconds, and that will tell you how much impulse I've given that box. Right. Increasing. The only thing to add to this then is this F is an average force. I am more than aware that in real life, forces are rarely truly constant. This equation still works if you just use an average force. And delta T is the time of collision, the time over which this force is applied. Increasing the time of collision for an impact force increases the resulting momentum change. Yeah, that makes sense. If you apply a force for longer, you'll get to impart more impulse to it, more momentum to it. The converse is increasing the time of collision for a fixed momentum change, i.e. the car crash, decreases the impact force. Good for not getting injured. So constant force, we've got force acted for a certain amount of time, multiply those two together. So on a force time graph, this is the impulse. Great. Ace. So no need to use average force because force was constant in this case. Nice. But if it's a varying force, then you're going to need to use some sort of average such that the area underneath this rectangle is equal to the area underneath this blue curve. And that's how you calculate the average force in this case. For those of you who do A-level maths, you'll realize that, or hopefully realize that rather than just multiplying a force by a time, you'll be looking at the integral of a force with respect to time. That's the most general statement. But as I said, for A-level physics, let's not get over excited. You don't need to know calculus. You don't need to do A-level maths. Just be aware that the most true general statement of impulse, it is a change in momentum, and it is equal to the area underneath a force time graph. This is also impulse. Great. We love it. And this is FAV. My FAV. Good. The impulse of a collision is equal to the area under the force time graph. Yes, couldn't say it better myself. Right, as promised, here's the exam question. How are we getting on for time? Oh, gosh, we're going to have to push on a little bit. Explain how crumple zones reduce the impact force to a driver using, well, we've sort of covered this already. The crumple zone gives way and collapses. This increases the impact time. The change of momentum is fixed. And so the average impact force is reduced, and then give the equation. Give the equation, it always helps. Right, conservation of momentum. Part of the reason we love momentum so much is because, like energy, it's conserved. As I said, this is I personally think it's quite a it's a slightly profound realization to recognize that although we always talk about energy, we're always going on about energy, not only specifically in physics, but also in politics and life in general. The only reason in physics we're actually interested in this artificial mathematical construct, you know, half mv squared, mgh, and all these, we've got like so many different mathematical expressions of energy that don't really seem to have anything mathematically to do with each other. The only reason we're interested in all those specific odd-shaped blocks of maths is because it happens to be conserved. If it wasn't conserved, there would be nothing particularly special about those equations. And the same is true of momentum. Momentum's nicer. It just looks nice, doesn't it? Mass times velocity. That, you know, that seems like it should work. Whereas energy is always a little, I don't know. This is, yeah, a slight personal philosophical insight, but yeah, the world's a beautiful place. Right, momentum. As you've probably been staring at for a couple of minutes now, momentum is equal to mass times velocity. During collisions, you can transfer momentum, but the total momentum in the system is always conserved, regardless of whether you're losing energy or not. The momentum's always conserved. So long as no external force acts. So if you've got two balls colliding, and so long as I don't, you know, rush in there and push one of the balls myself, the momentum will be conserved. Momentum is a vector quantity. It is a scalar, mass times a vector. So it is itself a vector. With direction, when considering a problem, we must select a direction to be positive. We've encountered this concept several times today. We need to establish a convention and stick with it. Right. For momentum questions, I know they seem simple. You know, you're talking about two balls. How bad can it be? It's pure hubris, I assure you. Be neat, be careful with your accounting for these questions. I don't mind whether you want to use different symbols for, you know, velocity or momentum afterwards and before, whatever works for you, but just make sure you don't get confused, because these questions can and rapidly do become a sort of quagmire of indices, these little numbers. So beforehand, the total momentum defining right as positive, P1 minus P2 equals P4 minus P3. Therefore, you have M1 v1 minus m2 v2 equals m2 v4 minus m1 v3. And then you can imagine once you start dividing those across, you can end up with all sorts of things, and they all look pretty similar, and yeah, horrible. Right, let's do an exam question, and then that should take us to the end of this session. We'll have a, I believe it's 15-minute break. Good, excellent. Okay, we're in the home stretch, don't worry. Consider the diagram below showing a rocket of mass. So as soon as you see rocket, you know it's something to do with conservation of momentum and Newton's third law, perhaps. Of mass, 7.5 tons, traveling through space at 60 meters per second. Fuel tank of mass. Oh, okay, so we've got two separate masses for the fuel tanker and the rocket itself. The rocket detaches the fuel tank, after which the fuel tank travels in the original direction of motion with velocity 45 meters per second. Determine the velocity of the rocket after the fuel tank detaches. Sweet, love it. Determine, that's our command word. It's in the category of calculation. 3 marks should be 3 stages. Okay, so before they're together, they're traveling at 60 meters per second, and their combined total is 39,500. Okay. They then separate, and we are told only about the case beforehand. Right, let's we've got mass of rocket and mass of tank. And we are going to want to, well, we've got V tank already, but let's call this V rocket. Lovely. So the total momentum before is equal to the total momentum after. Total momentum before, simply multiply these two numbers together. Lovely. Big number, but not to be feared. Right, after detachment, you've got 2 contributions. You've got the tank, which is lovely because we know both of these. Hooray, hooray, hooray. Afterward, and we've also got the rocket. We know what this is, but we don't know what this is. That is what we want. Okay, so we've got an expression in terms of V rocket. Last thing to do is set these equal to each other because momentum is conserved. Fab. Yeah, sorry, that's just rearrange. That's sort of just neatening up this line, and then we're equating the two. Okie dokie, rearrange for V rocket. It's 124 meters per second. Does that make sense? Looking back at my question, yes, it makes sense that this is going faster, not only than this, but also it should be going faster than this. Otherwise, detaching was an exercise in futility. The point of detaching is that the rocket can go faster. So our answer is still on the same order of magnitude, but it's bigger than 60 meters per second. Right, okie dokie. We don't generally go into the mini-mock papers unless we can avoid it. Those are for you to do in your own time and have a great time doing it.